So in this video, I'm going to work some more problems in preparation for the exam. I posted a video last Friday that had some problems on it, and I'm just going to add some more to it. Also, I posted a video that identified topics that could be on the exam, and of course, the problems I'll work here come from those topics. So I'm not going to do, for example, trig substitution because, with the one exception, sine squared and cosine squared, that subject is not going to be on the test. So I've chosen a problem, number 44, on page 561. So this is to find an antiderivative for the function 1 over x cubed minus x squared. So look closely there. This is a proper rational function. The degree of the numerator is 0. The degree of the denominator is 3. 3 is bigger than 0. So we have a technique for it. It's called partial fractions. And partial fractions, there are 3 cases that could be on this exam. And we know which case we are by factoring the denominator. So let's take a look. X cubed minus x squared. Really simple to factor, pull the x squared out, x minus 1. So you look at that, and we're definitely in case 2. We have a repeated linear right there, x times x. And we have another linear, x minus 1. So what we're going to do is decompose that function, and for case 2, the pattern goes like this. So we're working on the function 1 over x. Let's factor it. And our decomposition pattern is some constant over x plus another constant over x is the repeated factor. So x up to the power, of course, we'll stop at 2. And then we get another constant over the linear x minus 1. So the technique is next we want to equate numerators. I'll say equate tops. It's easier to write. So the top of the left is 1. Now notice this a is already over 1 power of x. So when I equate numerators here, I'm going to use the least common denominator, which is this denominator over here. So a, I only need to multiply it by the other x. That's kind of ugly. Let me clean it up. So a gets the other x, and he also gets the x minus 1. B is already over both x's, so B only needs x minus 1. C is over the x minus 1, but none of the x's. So using the least common denominator, I get that expression. And since we have 2 linear factors, we can plug in some well-chosen values. X equals 0 is one of them. On the left, I get 1. On the right, the first term goes away and the last term goes away. Leaves me, you plug in x equals 0, I get negative b, and therefore b is negative 1. The next thing we can do is plug in x equals 1. I still get 1 on the left. I always get 1 on the left. And now the first 2 terms go to 0, and I'm just left with c. So the self-solving equation, c equals 1. And finally, because we had case 2, we can't plug in a value and get all 3 of them, but notice that x here, a, gets involved with squares. So we'll pick on squares. I have none on the left. All I have is a constant. I get a of them out of that first term. Out of right here, I get none out of this guy, and I get c more of them back here. And since I know c equals 1, I know a equals negative 1. So, remember, we're working on this integral right here, and now I'm going to come down here and write what we figured out about it. It is equal to, then I'll slide this up, the integral Stay put. A was -1, so -1 over x. B was -1, so plus -1 over x squared. Just plugging in that guy right there, and C turned out to be +1. And hopefully you can look at all of those and say those are super simple antiderivatives. A little bit of sign issues. So the first one, I get a log. I get minus the log. This is an antiderivative, and so we need to include absolute value signs. We don't know the x values. Could be negative. And then on the second one here, I get a power function. I'll write over here, -1 over x squared is equal to -x to the -2. So raise the power by 1, takes me to -1, divide by it, and we end up with +1 over x. Right, raise the power, divide by the new power, so the minus signs cancel out, and we just get 1 over x. And then we get another log back here, ln, no tricks here, x minus 1 plus c, and there's our answer. All right, next problem. All right, changing directions fairly drastically. I've picked a problem out of the book number 38 on page 703. So this is from the chapter on infinite series, chapter 10, and it just simply asks, does this series converge or diverge? And here it is. The summation, k equals 1 to infinity, 2 to the k, times k minus 1 factorial, minus 1, divided by k factorial. So we want to settle the issue, and we want to do it with a test. So, whenever you see factorials involved, like the very first thing you should think of is the ratio test. I suppose we could make an example where the ratio test wouldn't satisfy it, but that's where we should start. So let's write here factorials implies the very first thing we're going to think about is the ratio test. So we're going to try it here. It's going to calculate the limit as k goes to infinity. The k plus first terms, so plug in k plus 1 for all of the k's. I'll simplify. K plus 1 minus 1 is k. And then we get a k plus 1 factorial. And then we divide by, or what we always do is invert and multiply when it's a fraction, and it almost always is. So k factorial divided by 2 to the k times k minus 1 factorial. All right, and then a lot of nice things happen here. The 2 to the k's, I have 2 to the k here, and one more there. So these guys all get canceled, and it leaves me 1, 2. Right there it is. Okay, and then I have k factorial over k plus 1 factorial. That guy is just k plus 1. So let's keep track of what's going on here while we go. I've got a 2 surviving. And then k factorial over k plus 1 is 1. Factorial is 1 over k plus 1. And a very similar thing happens here. I have k in the numerator, k minus 1. So k, the last k, will survive in the numerator. So k, let's say, divided by 1. And if you look closely at that, you should be able to tell the limit is 2. This is the ratio test. So what matters? 2 is bigger than 1. It diverges. Done. From the same page, here is another one. This one is number 42. Same instruction. We have a series 42, 2 plus minus 1 to the k divided by 2 to the k. All right. So this minus 1 to the k is it's a little bit of a nuisance. You need to think about it just a little bit. We know minus 1 to the k oscillates back and forth between minus 1 and 1, and therefore the numerator, call it the top, it's only 3 letters, it's going to range from 1 to 3. In fact, it is always 1 or 3. When k is a negative number, it's equal to 1. When k is a positive number, when k is an odd number, it's equal to 1. When k is an even integer, it's equal to 3. So it is always positive. So I think what we want to do here is use the comparison test, the ordinary comparison. You know, the minus 1 to the k, it causes a little bit of a problem when we take the limit. In fact, yeah, so we'll just use the ordinary comparison test, and here's how we justify it. We know the numerator, 2 plus minus 1 to the k, is always less than or equal to 3. And of course, it's always positive. Okay, 2 to the k is positive if I divide through by 2 to the k. Then notice I've built up in the middle here the series that we're trying to analyze, and I have it bounded above by this series for every term by term for every k. And if you add these guys up, add them all up, we have a geometric series. Which looks like this. 3 times 1/2 to the k. It converges. It's less than infinity because r equals 1/2, which is between 1 and negative 1. Now, we can actually find the number this geometric series converges to, and then we could know that the series we were given, it converges to a number less than that, but we're not really interested in the value. We're interested in determining its behavior, and we did it. It converges. All right. All right. This problem is representative of probably many out of the polar coordinate section, but it's not referencing a particular problem. Just one I chose, so I want to talk about graphing r equals 3 plus sine theta. Okay, and I've got a polar graph over here to draw all of our information on. The first thing we'll think about is the r values. Notice because sine theta goes between minus 1 and 1, then we can see that r is always going to be between 2 and 4. 3 plus 1, 3 minus 1. And so on our graph, we'll just think of these circles as being a unit distance apart. So 1 there, 2, 3, and finally 4. Okay, and remember, let me draw as best I can in red. Because r is always between 2 and 4, then if I find the circle, r equals 2, and then the circle r equals 4, I know the graph is totally contained between those circles. R can get no closer to the origin than 2 and no further away than 4. So no graph in here and no graph out here. It's all between 2 and 4. Okay, then we can just make a nice little chart here like I showed you. I think probably the book does this too. We'll go by quadrants. We'll identify theta. Theta goes 0 to pi over 2 in quadrant 1. Sine theta goes from 0 to 1. And then finally our function r goes from 3 to 4. Right, sine starts at 0, so 3 plus 0, and then ends up at 1, 3 plus 1. So we start here. Let's graph in blue, I guess. We start at 3. We end up at 4. And constantly, r moves further away from the origin. Sine is increasing, so r is increasing. And increasing in polar means further from the pole, from the origin. Now, there is one angle that's easy for us to do the arithmetic in our head. It's this angle right here, back to black. That's, if you look carefully at the polar coordinates, that's pi over 6. The sine of pi over 6 is 1/2. And so r is equal to 3.5. We've made it, by the time we get to pi over 6, we made it halfway between the circle at 3 and the circle at 4. Doing that in blue. So now we can draw our graph gradually away from the origin, eventually getting 4 units away. Quadrant 2 is pretty simple. We just retrace those steps. In fact, maybe we can just do it without identifying. We're just going back. So we're going to end up there at 5 pi over 6. We've made it halfway back, and so just keep graphing. Boom, something like that. All right, quadrant 3 in black. Theta goes from pi to 3 pi over 2. And sine goes from 0 to -1. And therefore, r goes from 3 to 2. 3 plus 0 is 3. 3 plus -1 is 2. So when we get through the third quadrant, we're back to this particular point. And once again, this angle 7 pi over 6, pi over 6 into quadrant 3. The sine is 1/2, so we made it halfway back. So we just keep moving closer to the origin. Eventually we get right there. And then I think it's fairly clear. We're just going to retrace that. So a little dimple here, kind of hard to see. This is an example of what we call a cardioid. And we've gotten it figured out. Really, really helpful was the, just to think for a second before we calculate it, like what are the r values? What can they range from and to? And it could be a lot more complicated than this. For example, if we had something like, we're not going to go very far with this, like 2 plus 7 cosine theta. Well, now the r values are going to go from where? -5 up to 9. So negative values means the graph's going to, every once in a while, pass through the pole. And so we recognize that there are complications here that we didn't have to deal with. And, we're not going to work this one all the way out. I just wrote it down here just for a contrast. All right, back in a minute. All right, on the last example, we worked our way through the graph of a cardioid, a rough version of it drawn to the right. And now I want to just work on it, the very same one. I want to find how much area does it enclose. Okay, so we have a formula for area. Here it is in polar coordinates. It's 1/2 the integral from alpha to beta r squared d theta. R is the polar function. So for us, that looks like 1/2 the integral. To trace out this cardioid, we have to go completely around the circle. So 0 to 2 pi, you could use symmetry, but there's no real advantage to be gained. So, sometimes you have to be tricky. Sometimes when you go 0 to 2 pi, it may trace the curve out twice, in which case the integral would be twice the value. But this was pretty straightforward. We didn't change the period of the sine. So therefore, to get the whole thing drawn, we need to go through the whole range. And also, it could get a little tricky if the curve passes through the pole, if r becomes negative, and that doesn't happen here. So this is a super straightforward problem, and all we have to do is integrate the function squared. Now there's a good chance on the exam I'll ask you, find an integral whose value is, whatever the area. And if that's what I ask, then we're done. There it is. But this particular time I didn't say that. I said find the enclosed area. So I'll go ahead and evaluate it. The first thing we need to do is square that function out. And hopefully that's nice and easy. 9 plus 6 sine theta plus sine squared theta. D theta. And so we get two easy antiderivatives, and then we run into that guy that we're memorizing. So thank goodness we haven't memorized. So we get 1/2. The antiderivative of 9 is 9 theta. Of 6 sine theta is minus 6 cosine theta. And then the antiderivative of sine squared, we know 1/2 theta minus 1/2 sine 2 theta. Yeah, and I did remind you that we're memorizing that. So it's no big deal. We can just write it out. And now we have the arithmetic to do. See if we can do it correctly. Plug in pi over 2 gets me 18 pi right there. The cosine of 2 pi is 1. So I get minus 6 from this guy. And then I get plus 1/2. Theta, again, we're plugging in 2 pi. And then we have minus 1/2. The sine of 4 pi is 0. And then we need to plug in 0. We identify in red. We're plugging in 0 now. And when you plug in 0 here, you get 0. When you plug in 0 back here, all of this, you get 0. But you don't get 0 here. The cosine of 0 is 1. So back to black. We're going to subtract negative 6. 0 minus 6 plus 0. I believe that's right. And 1/2 is times the whole thing. I think we need a parenthesis at the end. And do the arithmetic here. So let's count up the pi's. We have 18 pi here, and then it appears we gain one more. Actually, let's break it down into a couple of steps. Sorry, I got a phone call there, but I'm back. Minus 6 plus pi right here, and then this 0 keeps us from getting, then we get plus 6 more. So the 6's cancel. It appears that we are getting 19 pi divided by 2. And we can see that's a reasonable answer. The graph is totally contained inside a circle of radius 4. So therefore, we know that the area that we're trying to calculate it has to be smaller than the area in a circle of radius 4, which is 16 pi. And it totally contains a circle of radius 2. This circle right here. So it's totally contained by a circle of radius 4 and totally contains a circle of radius 2. So that means the area we're looking for has to be somewhere between 4 pi and 16 pi. And if you look at our answer, let's give everybody a denominator of 2. Okay. You can see we get an answer right smack dab between them. So I feel really good about it. Now, here's our answer. Over here, I'm just kind of thinking to myself, is that a reasonable answer? And, if I would have gotten an answer bigger than 16 pi or less than 4 pi, then I know it's totally unreasonable. Doesn't guarantee it's right, but at least ensures that it's it could be a right answer. And hopefully we didn't make any mistake there, and it is exactly the right answer, 19 pi over 2. All right, here's another problem, number 17 on page 763. I don't think I assigned this. Even if I did, maybe it would be an okay thing for us to talk about. So let me read the problem to you. This section is from 12.1, parametric equations. It says part A, eliminate the parameter to obtain an equation in x and y, and then describe the curve. Hopefully, we eliminate the parameter, we recognize the curve. And so the way, there's lots of ways we can do it. I think for this one, let's just take the y equation and solve it for t. So the square root of t is 1/3 y. And now, I might normally square that, except I got a square root of t sitting right there. I could solve it for t by squaring, but why not just plug in what we got right there? And so I get right there. So x equals the square root of t, which is 1/3 y, plus 4 more. And now, hopefully you recognize that. That is the equation of a line. Let's solve for y. Write it in slope-intercept form. So 1/3 y equals x minus 4, and therefore y is equal to 3x minus 12. Multiply through by 3. So that is a line. The slope is 3. The y-intercept is negative 12. But we have a few restrictions here. X is always bigger than or equal to 4. Square root t is positive, and y is never, ever negative. So when we talk about the curve defined by this set of parametric equations, we can say it's on the line. It is not the line, the whole thing. Rather, it is on the line. And so we need to say just a little bit more. The line we got has slope 3, intercept negative 12. Let's find out where we are. Notice we have a range of t values. So if t equals 0, x equals 4, and y equals 0. And at the opposite end, t equals 16, x equals 8, and y equals 12. The square root of 16 is 4 times 3. So let me draw axes that better fit that information. So we need to go from the point 4, 0, that guy, to the point 8 comma 12. And we need to do it on that line. So the point 4 comma 0 and the point 8 comma 12. So the graph is that. The actual line goes on. But the curve that we've been given for these t values this portion of the line, and we have the information here when t equals 0, the smallest t, we're at this point, and therefore the orientation is this direction. And there you have it.